whole bunch of patterns. And patterns leads well into what we're going to do today. So let's look at the first one. 7, 14, 21. What's going on? Adding 7. We're adding 7. And so what would the next term be? 28. Okay, number 2. Who sees it? Matt?
It's like 1 to the third, 2 to the third, 3 to the third.
Yes, they are our cubes, aren't they? So what's the next one? It's the cubes that you memorized on your summer work.
Oh, yeah.
Just say yes, ma'am.
No.
1 cubed is 1. 2 cubed is 8. 3 cubed is 27. Thank you. All right, 64. All right. What's the pattern of 3? Adding 4. Okay, so the next term is? 23. Okay. Who sees the pattern here? Okay, what do you think?
-4.
All right, Cade says, so this is minus
I'm stupid.
6, and this is -4. Next one would be -2. Okay, so my next term would be 6. Or, does anybody see a different pattern? All right, good. Multiplying by 2/3.
That's a good thing.
I did 2 more.
Okay, ooh, good. I heard somebody say exponential. Thank you, Simon. Very good. So these were adding a constant every time. What could that be considered? Linear. This is multiplying by the same number over and over again. It is exponential. All right. So if we did it this way, we'd say our next term is 16/3. 16/3 if we thought it was multiplying by 2/3. Okay. This one was a little trickier. What do you think on this one?
Never mind. You guys. It's an S.
Oh, for number 5?
Yes, Ryan. That's the one I've been on.
Okay, what do you think, Ryan?
Is it 3 or times 3 minus 2?
It sure is. Times 3 minus 2. Times 3 minus 2. So, 8 times 3 is 24. Minus 2 is 22. 22 times 3 is 66. Minus 2 is 64. 64 times 3 minus 2 is 190. So, now that you know that, and since none of us have our calculators, you're waiting for me to write the answer on the board. There you go, 568. Okay, so this one, you probably can't see this one yet because we haven't done much of this. But do you see if I multiply that 3x by x plus 5, we get this?
No.
I did not see
Oh, okay, distribute. Come on now. 3x times x is 3x squared. 3x times 5 is 15x. So in this one, we're multiplying by x plus 5. And so my next term would be a little complex looking, slightly. It would be this.
Are we going to figure that out?
No. Okay, now 1 through 5 are all doable for you guys. 1 through 5 are quite doable. Okay? Now, I didn't give you any direction on this one. So you could have gone 2 ways with it. You could have said point up, then point down. Then another point up, then another point down. And you could have just drawn it. Or, what if you had counted the sides?
Which I did.
5. And then this one was 9. And then this one is 13. So the next one would be 17. You could have gone either way with it. I didn't give you direction. Did anybody come up with a different way other than those 2? No? All right. So today, we're going to start looking at patterns of numbers, specifically sequences. Sequences of numbers. And since this goes into our Unit 4, we're going to focus on 2 types of sequences. The one that had the constant adding, so it would be like the constant rate of change. An arithmetic sequence. And one we
Yeah.
Well, damn it.
Ew.
A tingling right here. It's gone.
Okay. The other thing I want to look at real quick is my website real fast. What do I post on my website? The calendar. Okay, so yeah, you're right. Everything, the homework, the calendar, everything. All right, coordinate algebra. There we are. We're in Unit 4, but we just started the second part of Unit 4, sequences. So do you see how it has a subpage for Part 2 of Unit 4? If we click on that, the only thing I have right now is the new calendar. And then this afternoon I'll post today's notes. So let's take a look. Today we're doing arithmetic. Tomorrow we're doing geometric. Monday we're doing a learning task, which is pretty cool. Tuesday we're going to do an extension and do some more difficult problems with our arithmetic and geometric. And then Wednesday we will start our mixed review, finish it on Thursday, and we'll test on Friday. So it's a really small unit. There's no quiz, and this will be a smaller point value test. Okay? Any questions on the next 7 days? Because that's all I have. All right. And do you see workbook today, workbook tomorrow, learning task Monday, and then worksheet, book Wednesday. Do you see how you could use this calendar to know what to bring to class?
Yeah.
It'd be nice to have the right stuff.
Yeah, it's nice.
Okay. All right, back to our lesson then. Okay, so sequences, and specifically we're going to look at arithmetic sequences in a moment. But our warm-up had all different kinds of sequences. So what is a sequence? A sequence is simply an ordered list of numbers. And the first whole part of this is just going over the vocabulary that I'm going to use in class, the terminology I'll use in class, the terminology I'll use when I write your test. So let's make sure we all understand what I'm asking for. Yes, Kate?
I just thought of this. If letters have an alphabet, then what do numbers have? Like, what's the name for it?
They have
We have different sets of numbers.
Number
Or
bed.
number line.
Number line?
We also have the number line, but we have lots of different sets of numbers.
If you print it out, then you have
And we're actually about to talk about one of the sets of numbers. Okay, a term. A term is what we name a number that is in the sequence.
God, my elbow's been hurting me all day.
Now, here I labeled this a sub 1, and here I labeled this a sub 2, and here I labeled this a sub n. And the reason I did that is because today we're really only looking at arithmetic sequences. But I could also label this t sub 1 to represent the first term without telling you it's arithmetic. Or I could call this t sub 2 to represent the second term. Or I could call this t sub n. And I'm going to use this interchangeably. On your test, I'm just going to use t, because t doesn't give you a hint about whether it's arithmetic or geometric, right? And so you have to kind of do a little more investigating and figure things out.
Is A always arithmetic?
No, I wouldn't say always, but a lot of times. Okay, so we're going to let the sub 1 part means it's the first term. The t sub 2 would represent the second term. And t sub n represents any number of term in the sequence. Sometimes we even use that to represent the last term, the nth term. Okay, so let's go back to our warm-up real quick. All right, in this problem, what is t sub 3? 21. The third term is 21. So when you see this, t sub 3, that's what you're saying. The third term in the sequence is 21. What is t sub 1?
One.
1. Because the first term in the sequence is 1. Got it?
Yes, ma'am.
All right. Finite versus infinite. I think you already know the difference between these definitions. What does finite mean? Yes, Matt?
It's not infinite.
Nice.
That's true. So since it's not infinite, then it would end, wouldn't it?
Yeah.
Okay.
You would say N.
I thought that was a good answer, actually. I didn't realize you guys were making fun of me.
Well, it was actually good.
Okay. So a finite sequence is a sequence that ends versus an infinite one would be a sequence that
It's not N.
does not end, that continues, that never ends. Okay, so I'm just going to make up a quick sequence real quick. Okay, now we have a finite sequence. How many terms are there in that sequence? 4. What is t sub 2? 5. The second term is 5. Good. All right, now if I took that same sequence and I added the dot, dot, dots, what does that mean?
Infinite.
It goes on forever. It's infinite. What's a special name for the dot, dot, dot?
Ellipses.
Ellipses. Very good. All right, now ellipses can actually be used when we have a finite sequence. If I went dot, 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 but then I said, whoops, last term is 32. So all that's saying is, this is my pattern. I just don't feel like writing every number, and I'm stopping here. So this is still finite because it has an end. This one is infinite because it doesn't. Questions about that? All right, so once again, 2 different types we're studying, arithmetic and geometric. Arithmetic is where we add the same number each time. And that number that we add every time has a special name. It's actually, we represent it with the letter D because that represents a common difference. Now, why do we call it a common difference? Different. If it's what we add each time.
Because it's different.
Subtract 2 numbers, you get that.
Because if we subtract 2 numbers, we would get that. Do you see if I take any number and subtract the number before it, I get the common difference. So 5 minus 2 is 3. 8 minus 5 is 3. 11 minus 8 is 3. What is the common difference? 3. Okay, and an arithmetic sequence can be modeled by, if we have a common difference, what kind of function will model an arithmetic? Okay, what do you think?
Linear.
Linear function. It's modeled by that linear function because the linear function has a constant rate of change, doesn't it? Just like this does. All right, now geometric is a little different. Instead of adding the same number each time, we are multiplying.
Yeah.
And this is the one we'll look at tomorrow. We're multiplying by the same number each time.
Thank you.
Okay, and this is actually represented by an R for a common ratio. Because if we take, on a geometric, if we take any term and divide it by the term in front of it, that gives us the common ratio. Now, since we're multiplying by the same thing every time, like when we had those problems we just did when we were doubling something or taking half every time, how can it be modeled? Good. It is modeled by an exponential function. Yes, sir.
Oh, is that hyphen? Is that a minus sign or is that a?
It's just a hyphen.
Okay. Sweet.
I don't know how to. Okay. Now we talked about a sub n up here and how n represents the nth term. So n can either be one of two things. The position in a sequence. Where does it fall? Is it the first term? Is it the 8th term? Is it the 32nd term? Or it can represent the number of terms in a series. Now, series is where we just sum up a sequence, where we add it up. Now, this we will not do until next year. You will revisit next year. We are not doing it this year. Because when we find the sum of what we are studying this year, an arithmetic sequence, Matt, when we do the sum of that, it ends up being this cool quadratic function. And quadratics we're going to study next year. All right, so let's take a look at this. Domain. What is domain, guys?
The x value.
The x value. But do we have an x value in a list? Not really. It's the input. And what represents the input in these problems? Well, that is represented by the position of the term. Is it the first term, the second term, the third term? Etc. Okay. Now, the domain of a sequence. Well, I just said numbers like, is it the first term, the second term, the third term, the fourth term, the fifth term, the sixth term? What's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, forever. What kind of numbers are they?
Whole numbers.
Well, whole numbers would have a start at 0.
Natural numbers.
Set of natural numbers. Very good. So, the domain of a sequence is a set of natural numbers. If that sequence is finite, then it's not the entire set of natural numbers. It would be a subset of that. So like for this one, let's say I gave you um, 2, 5, 8, and 11. Our domain would be 1, 2, 3, and 4. Because there's the first term, the second term, the third term, and the fourth term. Make sense? All right, range is our output. And our output in this case are just the terms themselves. So when we're looking specifically at the range of a sequence, it is the terms in the sequence. Yeah. Sure. All right, so in this example, our range would be, what were the terms in the sequence? 2, 5, 8, and 11. All right, so let's find the first 5 terms in this sequence. Now, n represents the position of the term. So if we wanted to find the first term, we would plug in 1. When we plug in 1, what do we get out? 7. So I could think of this as a table. And I'm plugging in positions here, and I'm getting out the value of the term. So when I plugged in 1, I got out 7. When I plug in 2, what do I get out?
10.
10, 3,
13.
good, 4,
16.
and finally 5.
19.
Yes. So I could write it like this in terms of a table. I could write it like this and identify them individually. The first term is 7. T sub 2 is 10. T sub 3 is 13. T sub 4 is 16. T sub 5 is 19. Or the easiest way is just to write it like a sequence. 7, 10, 13, 16, 19. There's a sequence.
I'm not.
So this is an infinite one, right?
I'm 14.
It would be if I didn't define it right here as just the first 5 terms.
Okay.
You are correct. It would be. All right, we have 2 types of formulas we can use. And the recursive formula is the one that's already in your brain. A recursive formula for an arithmetic sequence is a formula that is used to determine the next term of a sequence. Okay, and we do this by using one or more of the preceding terms. Now today we're going to do some very basic ones where we really only need one term. Now on Monday you're going to do this learning task, and one of the parts of the learning task is where you do the Fibonacci sequence, where you don't just use one but you use 2 preceding terms.
It makes
So that would be a recursive formula. Now here we are given a sequence. First of all, is it arithmetic? How do you know? You're adding the same number every time. Very good. Now we're supposed to find the recursive formula. So let me tell you what the recursive formula is. It's a 2-part formula. We need 2 parts. First part, we say we have to define what the first term is. T sub 1 equals whatever. Fill in the box. And then the second part is to find any term in the sequence. You take the 1 before it. Well, n minus 1 represents the 1 before it, and add the common difference. So we have to fill in both boxes. First we have to state what is the first term, and then we say, well, to get to any other term, you take the 1 before it and add the common difference. So in this case, what is the first term? -3. What do we do to the previous term to get the next one? +5. Now, this is great, and this is what your brain already does without even thinking about it when I ask you to tell me the next term. It does this. That's what your brain does. It goes, oh, well, we started at -3, and we've added 5 all the way to get to 12, so if I add 5 more, my next term is 17. Now, the problem with that thought process occurs when you take the SAT as an 11th grader or 10th grader. Some of y'all take PSAT again next year. And it says, what is the 95th term? And I have proctored the SAT and watched a child go, and thought, oh boy. Because how easy would it be to lose track of how many times you added 5? I would not. There's no way I'd get it right. So, fortunately for us, the recursive formula is not our only tool we have. There's another one, and we're about to develop it by thinking about the recursive formula. So flip over. We're going to look at this sequence. And we're going to develop the formula that's, to me, most helpful in this case. Recursive formula definitely has its place because not everything can be defined by an explicit formula. It is helpful, but not always extremely helpful. So here we go. Is this an arithmetic sequence?
Nope. Wait, let me look at my notes.
Yes.
Yes. It has a common difference, and what is that common difference? 4. Okay, so I'm going to define it this way. I'm going to say, all right, the first term is 2. Now let's go back to our rules for recursive and think about, okay, to get the second term, we're going to take that first term and add the common difference. What is the common difference? 4. Is that how we get the second term? Yep. So now I'm going to say to get the third term, we're going to take this second term and we're going to add another common difference, aren't we?
Yeah, obviously.
Yep.
Yes.
And to get the fourth term, we're going to take that third one. And we're going to add another common difference. And to get the fifth term, we're going to take that fourth term and we're going to add another common difference. So every time we added another common difference. Does that make sense? And that's exactly what happened up here. So let's see if we can develop a formula for this. Do you see that every single one of these, no matter what term we're finding, started with this 2? Well, what does 2 represent? The first term. So every single one of these has that first term in common, doesn't it? And then to the first term we added something. We added 4. 4, 4, 4, 4, 4. A whole lot of 4s. Well, what did 4 represent? The common difference. So we added to that some common differences. How many common differences?
1. Wait.
Here I added 1, but here I added 2, and here I added 3, and here I added 4. So this first one has no common differences. The next one has 1 common difference. The next one has 2. The next one has 3. The next one has 4. How do these numbers compare with my input? The number of the term, the position of the term. What do you see, Andrew?
Isn't it like n minus 1?
It is. What they have are n minus 1 common differences. And I can cheat because my little thing does this. You can't cheat, so you can put n minus 1 at the end. Yeah. I bet you wish your pencil could do this.
But it can't.
All right. So every time I did the first term, plus I added to that n minus 1 common differences. Whoops, I missed an F. There we go. And that is our formula. But normally when we write a formula, we write it symbolically. So symbolically, we would say, to find any term, you take the first term and add n minus 1 common differences to that. So a sub n, which is really the same as t sub n, represents the nth term, to find any term. So if I gave you this, or the SAT gave you this sequence, and asked you for the 95th term, this is how you do it. You'd say, okay, to find the 95th term, I take the first term, which is 2, and add, well, 95th minus 1 is 94 common differences. Isn't that a little quicker than doing plus, 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 plus on my calculator? But it is fun to proctor the SAT and watch students do that.
Is it fun to watch them struggle at cursive too? Because
I don't think it would be as fun.
Wait, what student did this?
Oh, you can laugh. Just not out loud. Just giggle on the inside. Okay.
Why did you help him?
You're not lying.
The SAT.
You remember that? No, here's
It would be nice to help him. Regardless of your
I don't do it to help people like right next to me.
That was close. That was close.
Okay. So all these things mean the same thing they meant on the previous page. So we're good. All right, so here's another one. Find an explicit formula to represent this sequence. So first of all, is it arithmetic? That's what we always have to check first. Plus 3, plus 3, plus 3. Yes, it is. So my first term is -4. My common difference is 3. My equation is this. To find any term, I do the first term plus n minus 1 times the common difference.
Yeah.
And this is quite helpful because to find the 47th term, I do the first term plus 47 minus 1 times 3.
That's your answer.
And I don't have to, well, I can actually simplify this. The 47th term is, I see calculators.
Don't tell me. Negative 4 plus 47.
134. We have a winner.
134, I called it.
Good.
All day today.
All right, you have been.
Why did
All right,
you like,
now, it is perfectly acceptable for you to leave your answer like this. But do you see that I could simplify this?
yeah.
For you guys, I probably wouldn't. I would leave it like this, especially if it was just short answer for me. There's no need to simplify it. But let's say you're taking end of course test, and you don't see any answers in this form. This is the simplified version of this equation. So they might have it represented like this. Does that work too?
Yeah.
If I plug in 1, do I get out negative 4?
Yes.
If I plug in 2, do I get out negative 1?
Yes.
Yeah. So they may have it written like this, or they may have it written like that. I'm not sure. They mean the same thing. But I would always start with this one. Start here, and if you have to, simplify it. If you don't, don't. All right, you try example 2.
I can handle it. I got it.
With the explicit formula?
Yes. And then find the 100th term.
The 100th term, I can handle that. Oh gosh.
What do you get?
I seriously thought I was going to see. Oh.
Yes, calculator is quite handy.
No.
Oh, my squeak of the week.
Are you practicing?
Freaking get
Okay, I didn't need a calculator because on this one, instead of converting this to 99, I just distributed the negative 5 right here. And I hope you will always pick the easiest method. And the easiest method is to distribute the 95 and get negative 500 plus 5.
I just plugged the equation.
That's a lot. And then negative 500 plus 30 is negative 470. See, I wouldn't have gotten up for a calculator on that one. Maybe on this one. Maybe. But not on that one.
Joke's on you. I'm sorry.
Very distracting.
I'm going to stop.
Okay, so did you write the formula? And can you get the answer?
Yes.
Okay. Let's write the recursive formula for this one. What would the recursive formula be? T sub 1 equals
5 and
25.
There, got it.
T sub n equals T sub n minus 1 plus the common difference. What's the common difference?
5.
Negative 5.
Negative.
Okay, so there's recursive. There's explicit. All right, and here's the answer.
Wait, explicit.
Explicit is this one right here. See? It's in the
I don't remember
box.
Talking about explicit.
Explicit is in the box. Recursive is the two-parter.
Oh yeah. That one.
What
Yeah.
does recursive formula find?
Recursive formula helps you find the next term. But sometimes the recursive formula is the only way to go because you can't write it as an explicit. All right, so tonight's homework is out of your coordinate algebra workbook. That's not your book, that's a workbook. So on page 195, we're going to do all of them, but I'm changing the directions up a little bit. On 5 through 10, the first thing I want you to do is practice writing the recursive and explicit formulas. So for 5 through 10, write the formula first and then solve.
I'm confused between explicit and recursive.
Well, look at your notes and you'll be unconfused.
But I thought that we were doing a